Hi Year 12. So just before we start on to the new stuff that we're looking at today, I want to give you a quick recap on what we were learning just before half term there. Okay, so basically whenever you have a wire and it is moved, and that's key, keep remembering that because that's going to come up a lot today, it is moving within a magnetic field, then a current starts to flow. So it doesn't have to be the wire that's moving, it can be the magnetic field that's moving, as long as the two things are moving relative to each other. So you can either produce a current by moving a wire in a magnetic field or moving a magnetic field near a wire. Okay, so that was whenever we looked at this. This is page 227 by the way in our notes if you want to be following along. So if we have a coil of wire and we move a magnet inside the coil, then we're going to get a current flowing. As soon as the magnet is stationary and the two things, well, I suppose the two things are stationary, neither one is moving relative to the other, no current flows. If the magnet was moved out the other way, if you remember that, then the current flows in the opposite direction. Okay, so magnetic field, wire, if one of those things is moving, like near or within the other one, you're going to get a current flowing. Then we went on and we looked at the AC generator. That actually isn't important for us to remember how that works for today's stuff. We just need to remember that whenever either the wire or a magnetic field is moving, then a current is induced in the wire. So now on to today's stuff. If you open your notes at page 235 for me please, we're going to have a wee look at this, which is the basis for transformers, which we'll look at next day. Oh, I've just realised I forgot to do a retrieval roulette. Okay, just before I start talking about this, I should just remind you that if you have current flowing in a wire, that produces a magnetic field, and this is also key, the more current that is flowing, the bigger the magnetic field. Okay, so they're the two things that are key here, that current flowing in a wire produces its own magnetic field. If you have a wire and it moves across a magnetic field, current is induced in it, and this here combines those two effects. It's really quite clever actually. So right, let's look at what on earth is even going on in this here. This is a wee iron ring, and that's just like the iron core to increase the strength of the magnetic field. Okay, so we've got these wires. On this side, the right hand side, we've got a battery which is connected to a switch, and then we have a coil of wire. Now these wires are insulated like those ones that we use in school, or the ones that are on appliances in your house. So it's not that the current flows along this wire or this ring. This ring is literally just there to increase the strength of the magnetic field. Okay, so we've got one little circuit here with a power supply, a switch and a coil of wire. Over here we have a completely separate circuit, okay, and it's just a wire connected to a center 0 ammeter. Okay, so 0 is in the center. If current is flowing one way, it'll move one way, and if current is flowing in the other direction, it'll show the current as like a negative. Okay, two completely separate circuits, but one really cool thing that happens is if this switch is pressed, right, current is going to start to flow in this little right hand circuit. Yeah, so if we close this switch, then the current in this wire here is going to go from 0 to, let's say, 5 amps, right? So in the time immediately after this switch is pressed, current is going to grow from 0 up to 5 amps. Now, remember, whenever you have current flowing in a wire, you get a magnetic field. And the more current that's flowing, the bigger the magnetic field. So what happens is we end up with going from 0 magnetic field and then a magnetic field growing out of this Okay, so as that current goes from 0 to my imaginary 5 amps, the magnetic field that is being produced is getting bigger because the size of the current is getting bigger, right? So it's going to grow out. Now, hopefully you can see there, I keep doing this, like it's growing out, right? Whenever we're in class, I spend the whole time doing that, but I think showing you here is actually maybe a wee bit better. So the current is going to, or sorry, the magnetic field is going to grow out from this. Now, do you notice that it's moving across this? So that means that over here we have a magnetic field which is moving relative to a wire. So what's going to happen here? We're going to get a wee slight bit of current flowing in here. Now, do you remember that key I said at the very start? Current is only induced whenever the wire or the magnetic field is moving. So back over to this one again. As soon as that current is stationary, like a flat 5 amps, then there's no more current getting induced in here. So whenever you press this switch and the current goes from 0 to 5 amps, magnetic field goes out. As that is happening, you're going to get a little, like a wee flick of current in this one. But as soon as that current is stationary, this will go back to 0 because the magnetic field lines are no longer cutting across this wire. So they're not moving relative to each other anymore. Hopefully you're getting that. Now, let's say we turn this switch off. What's going to happen to the size of the current? It's going to go from 5 to 0. So what's going to happen to the magnetic field that it's producing? It's going to go from here to here. Or it's going to go from here all the way back in here. Now, hopefully you're picking up that then the magnetic field lines were cutting back across this one in the opposite direction. So you're going to get another little wee flick of current, but this time in the opposite direction. Okay, this is a tricky thing for people to understand, right? So I'm going to go over it again, not even apologising for that. So from the start, if we turn this switch on, current is going to grow from 0 to 5 amps. I've just made up the 5 amps, right? I'm just using that as an example. So it's going from 0 to 5 amps. Whenever that happens, magnetic field grows out from it, cuts across here, induces a current there. As soon as that is a steady 5 amps over here, the magnetic field lines are stationary, right? Nothing's happening, literally nothing is happening over here anymore. So this little ammeter showing the current that's in this circuit is going to show 0 until we turn the switch off again, magnetic field back in. So we've cut back across here, so we're going to get another little small current induced here, but it's going to be in the opposite direction, because whenever it was growing out, magnetic field lines were going this way. Whenever it was coming back in, magnetic field lines were going this way. So we end up getting a wee bit of current this way, and then a wee bit of current that way. Now, if we were to sit and continuously press this switch or turn it backwards and forwards, then your magnetic field lines would be, from over here, they would be growing and shrinking and growing and shrinking and growing and shrinking. And even though the current that's being induced in this one here is always going to be in the same direction, because this is a DC battery, so turn this on and off and on and off and on and off and on and off, all you're doing is increasing the current from 0 to 5, back to 0 to 5, back to 0 to 5 in this here. But because of that on and off and on and off and on and off, the magnetic field that's produced by the current in this wire is going to be growing and shrinking and growing and shrinking and growing and shrinking and growing and shrinking. So what you would end up with here is like your current would be going like that, 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 right? And you remember what a current that's consistently changing direction is called? Alternating current. Now, this is the basis of a transformer, and as I say, I'm not going to try and do too much all at once here. We'll do that next lesson, the transformer stuff. We'll do this. For today, all I want you to get your head around is this Faraday's iron ring experiment. Now, Hopefully I have done an amazing job explaining that there. However, if I haven't, I'm going to read through this with you, right? I know that's like not the best, but I'm going to read through it and we'll stop and talk as we go. Okay? So, Michael Faraday's iron ring experiment is one of the classic experiments from the 19th century. Look at this diagram. The soft iron ring in the centre has two coils wrapped around it. That wee eye is missing there, look. Put that back in. Okay, two coils wrapped around it. The coil on the right is connected to a switch and a small battery. The coil on the left is connected to a centre 0 ammeter. The coils are made of insulated copper wire, so no current can ever flow in the iron ring. In the situation shown in here, there's no current flowing in either coil. So what happens when the switch is closed? A current immediately flows in the coil on the right, but Faraday observed that there was a momentary deflection in the centre 0 ammeter. How could this be explained? Before we go on to read it, I'm hoping you're already sort of explaining that in your head. Yeah, because it's all the stuff that we've just talked about. You might want to rewatch my amazing explanations a couple of times. Okay, so Faraday argued closing the switch caused an increase in the current in the right hand coil. This is doing my head in that they're on separate pages and I can't go back to this. This caused an increasing magnetic field in the right hand coil. Since the iron core links the two coils magnetically, there is an increasing magnetic field in the left hand coil. The increasing magnetic field in the left hand coil caused an induced current which flowed through the ammeter. The effect is momentary. When there's a deflection of the ammeter needle, there is a deflection of the ammeter needle only when the current in the right hand coil is changing. I'm going to highlight that. When there's a steady current in the right hand coil, there's steady magnetic field in both coils. For induction to occur, we need the current in the left hand coil to be changing. I'm going to maybe highlight this whole thing. Yeah. Steady current in right hand coil, steady magnetic field in both coils. For induction, we need current to be changing. Okay, when that happens, what happens when the switch is opened? There's a momentary deflection in the ammeter needle, but this time it's in the opposite direction because the field in the left hand coil is now decreasing. This simple experiment is the basis for the transformer, without which electrical energy could not be transmitted efficiently from a power station to our homes. So, do take your time to make sure you get that before you start on to these questions. I'm going to have a wee look at the questions and see if there's any that I need to give you any wee hints for. Okay, so this one here is just talking about electromagnetic induction. So, inducing a current using a magnet. Let's see this little bit explain these observations. Don't be getting too worried about that. It's more like you don't have to say why it happens, which I know seems silly for explain, but for that one, I don't want to just give you an answer. For that one, all I would be saying is that whenever a magnetic field and wire are moved relative to each other, a current is induced in the wire. That's spoiler, that is what I'm going to put for that one. Okay, so this one is just what I have been rambling on about there, so not doing any more hints for that. Ooh, this is a good wee one. I kind of touched on that, but not really, sort of. Remember I said about turning the switch on and off to save you from doing that. What type of current could you have in that first one instead? And you know what? I'm going to tell you to leave out 11, 12 and 13. Let me see. Actually, no. This here, I'm answering it as if it's like, I would answer as if the magnet moving into the coil. So back away from, sorry, I'm going to ignore what I've just said. So see from 11, that's back talking about this first little one again, I think. Okay, so answer it for this. It's not about this anymore. Yeah, 11, 12 and 13. These are all about the diagram in question 9. Okay, I think, anyway. Now, once you've got that done, I want you to use your self-quizzing book to try and get somewhat caught up. I'm going to give you some specific pages to have a wee go at here, okay? So this one here, the second booklet, so not the one that is on space, waves and light, the other one on the near stuff. And see if we go to, do you know what, this one here, so section 24, electromagnetism 1, there's your questions and your model answers. And then on the next page, oh dear, there's space for you to, basically, first of all, copy that across and then try and do it from memory. So doing that properly will take some time, so do it properly. And I would quite like you to do that for the electromagnetism 2 as well, okay? So again, I'm going to write this all in the lesson anyway, but electromagnetism 1 and electromagnetism 2. Spend the rest of the lesson doing self-quizzing on those two sets of pages. Okay? I think that is me. I will see you next day. Bye.